Thank you all. Thank you, Liliana and Alberto. And thank you all for coming back from coffee and resisting the repeated attempts to sabotage the attendance of the last talk, which I will, try to disregard for now. So I was asked to give a talk on, how we can direct the orchestra of real-world data. And obviously, real-world data is something that we'll see more and more in the years to come. And this is an area of science and methodology that I'm much more akin to, since it is part of what I do almost on a daily basis. For those of you who don't know me, despite being a practicing clinician, I also have qualifications in epidemiology and biostatistics. And for good 7 years, I was working in the largest center for big data in health in Australia and the world, and that was a very, very useful experience. So these are my disclosures again, and I'll start with some basic concepts, and I hope we'll all agree on. So I won't I won't insist too much. So what is science? Well, science is the knowledge based on demonstrable and reproducible evidence. And it seems a very simple definition. What we tend many times to forget is that the word reproducible is key. The scientific method involves observing, making that type of eureka discovery. People say that most of the most amazing discoveries that have saved thousands or hundreds of thousands or even millions of lives become with someone thinking, that's funny. And after you do have that uncanny sort of hypothesis formed in your mind, then you obviously decide to test the hypothesis, because we're full of circumstantial evidence and full of creating patterns in our brain that are actually spurious, that are actually non-existent. So we do the study, we organize it, and we design it in a way where we can truly prove whether it is what it needs to be, and we test the hypothesis. And based on the results of the study we've designed, we can actually accept or reject the hypothesis. And that's what we published and we communicate to our colleagues, and that's how the body of evidence grows. But probably one of the most crucial, if not the most crucial aspect of science is reproducing the experiment. There are some people that suggest that you can find almost in the scientific literature at least one study to support the craziest of all notions of hypothesis. But that doesn't make it true. So it's important for us to know that something is true and is as close to the truth as possible, that it is reproduced. So if something is not reproducible, it's not scientific. And this is a cycle of research, and this is where we all sort of stand, and everyone comes from a different perspective. Some are hardcore clinicians, others are epidemiologists and look at more population-based studies. Others are scientists and work in the lab and the bench all the time. So depending on where you are, you could, for example, be doing basic research, and then based on like a new mechanism or pathway you've discovered, to be able to translate it into some type of intervention for humans. Obviously, this would need to be tested in the context of clinical trials, and if successful, then it can be incorporated in clinical practice. And as we do clinical practice, obviously, many times we'll do what we call phase 4 studies, or studies where we'll confirm whether what has been observed in RCTs actually applies to our population as well. But some other times we might have an interesting idea just by doing, a retrospective study. And that retrospective study then could lead to a hypothesis which, could enter the cycle of research here and lead to what we call a reverse translation. So that's why it's a cycle, because you can essentially enter at any point. And this is the traditional evidence-based pyramid, the hierarchy of evidence-based medicine, where you can see that, editorials and expert opinions like the ones you hear today, when they're not backed by evidence, but it's just expert opinions, they do not rank very highly. When you have case series, case reports, then case control studies, and obviously at the pinnacle, at the very top of this pyramid, we have systematic reviews, but not any systematic reviews, good quality systematic reviews of a good number of properly powered and properly designed RCTs. And I say that because many people forget that, and they think that all systematic reviews and meta-analysis are the same, which is hardly the case. However, traditional evidence-based medicine for a few years now has been under attack. And what's the reason behind that? Many people say that it's lots of sand and nothing more, and it's not what we thought it would be. So the actual reasons are because evidence-based medicine, according to the proponents of this idea, has actually failed to deliver, failed to produce tangible improvements in outcomes that really are relevant to patients, despite all the funding and the time we have delivered. And people think that the paradigm of evidence-based medicine, and particularly RCTs, is a bit, antiquated and does not serve patients well. Why? Because of the huge cost, of the logistical nightmare that it is to design an RCT. Some of us here have done it and know how painful it can be. Of the time it involves, we start something today and we might not have the results for 3 to 4 years if we're lucky. Of the statistical methods used, the inferential framework, which essentially in most cases would allow you to spend so much money and probably have power to test or to answer just one question. Which means that many times the sample size is very, very big, and the whole generalizability, like how easily can we extrapolate, can we transport the results of the RCT to the population that we treat every day in our clinics. And this has led many to suggest that, well, we have a better solution. And that solution is the era of big medicine, of big data, of real-world medicine. And that's a very interesting concept. Why? Because it seems very appealing at first, and there are distinct advantages and disadvantages that I will be, discussing in the next few slides. So what is big data or real-world evidence? Because real-world evidence, anything can be real-world evidence, but I think in modern epidemiology, we almost tie it with big data. So big data in healthcare can actually be produced by anything. Can be, from the records, the hospital records, or your clinic records, your lab records, but at the same time from wearables, from, medicine dispensation records, from other research studies, generic databases, genomic data studies, all the things that you see here can be contributing to that big pool that is called big data in healthcare. And, what makes it appealing is that if we really had invested as much time in real-world evidence and big data, we might actually have had better results, much, much sooner. This has been published and say, the whole, I imagine most of you know the rofecoxib scandal or debacle, where essentially many patients were put at risk because due to our research methods, we failed to identify specific subpopulations that would actually be at risk by taking this non-steroidal anti-inflammatory drug. So if we had utilized big data, having records of 100 million patients for safety would probably, lead to the discoveries that eventually led to, this drug not longer being available. And this would have taken 3 months, than 5 years. And probably many lives would have been saved. And at the same time, if this is a theoretical example, we actually have very, solid, tangible examples where a pan-Nordic study that examined more than 1 million pregnancies with exposure to, and some of them had exposure to SSRIs, quite convincingly was able to show that, what we feared, that SSRIs are teratogenic, it's actually not true. So that means that now women who have some type of depression or depressive disorder and need their medication while being pregnant, they can, be reassured that this is not likely to increase the chances of their baby having some congenital anomaly. So what is the promise of big data? Why do we think it's relevant for us? Well, the first thing is that it is real-world data coming from real patients. It's not optimal patients, it's not IVF-naive patients, it's the patients that we see every day in the clinic. And it is essentially an accumulated repository of data from real-world settings, and therefore not, again, ideal conditions that might not be as informative. And in many cases, someone would say they can reflect how an actual intervention might work in real-world setting. And why is that important? Imagine that we have a new surgical technique, which RCTs show that it's fantastic. Well, if you're not trained in that specific surgical technique, it might not be good for you to apply that surgical technique to your patients, but it might be better for you to stick to what you know. Of course, having large sample sizes can be a blessing or a curse, but in terms of a blessing, means that we now have sufficiently large data sets to allow for complex analysis, to be able to detect clinically significant but yet small for some differences. And importantly, and we've seen that with the Poseidon group, with the Aphrodite criteria, we do have subgroup of patients that behave differently and therefore could benefit differently from different interventions. So having sufficiently large data sets means that now we are powered to see these effects across these subgroups of individuals. What else is there to discuss about big data and real-world evidence? Where we have comprehensive multi-dimensional data sets from various sources, which might better reflect the interaction between patients, their characteristics, baseline characteristics, intervention, environment, genes, and so on. Of course, we have challenges that come also with big data. And that's why I said not all is perfect with big data or real-world evidence. We have a large volume of data that creates specific analytical problems, and we need powerful computers. In the Center for Big Data I used to work, just to give you an example, we used to run complex modeling in not that of a big data set. It involved about 1 million observations, which I know might sound impressive, but it's not as impressive. And specific models that we used to run, and they were run in an array, so in like a mini supercomputer in a way. They used to take 2 weeks to have the output. And sometimes the output would be, oh, I'm sorry, the model did not converge, and therefore we would need another 2 weeks to be able to refine that model. So you can understand that that can be a very, very complex exercise. We need advanced statistical techniques, and it can, as I just demonstrated, be very time-consuming. And probably the key risk for me, which I already have seen, published, is studies where they find statistical significance in clinically insignificant differences, and all of a sudden, instead of trivializing it, they're making a big thing out of the statistical significance. If it's not clinically significant, it doesn't matter how statistically significant something is. Of course, the other big problem with big data is that we have what we call variety and veracity, which means that the data are not really good quality. They're not captured for research purposes. They're not standardized. Many times they're not clean, which means you have to recode them, you have to clean them, and that can take months. That can really take months. And just because we have these type of issues, they are vulnerable to systematic error. And that's another big point about big data. Big data can mean bad data, and bad data, it doesn't matter how great your statistical analysis is, it will still lead to garbage results. So have that in mind. Just because a study is big doesn't mean that the people who analyzed it knew exactly what they were doing, and at the same time, just because it has been published in a very good journal according to your standards, don't assume for a fact that everything is perfect. Always stand critically with any paper that you see published, particularly something that doesn't seem to make sense. We have obviously evidence. This is coming from the Ioannidis group, where essentially they have seen that just by analyzing real-world evidence, you can have inflated effect sizes compared to if you did randomized controlled trials. And again, this is a risk with real-world evidence that we need to always have in mind. Of course, these data, as I said, are very expensive to collect and manage and analyze. Therefore, that costliness many times hurts any type of attempt to create a big enough data repository. In Australia, for example, we have federal funding. If we didn't have federal funding, which we have for another 7 years now, we would have big issues potentially securing research grants to, be able to, secure the viability of our databases and all our staff, our data scientists and so on. And of course, with big data, when you're collecting them, there are always concerns about cybersecurity, privacy, confidentiality. These are not data that patients have signed off to be used for research, so you need to ensure that you comply by local laws and regulations. So is big data and real-world evidence relevant for reproductive medicine? Of course. We're probably one of the best fields that big data and real-world evidence can be useful. Why? Well, because we have complexity of data sources and we have a multi-stage treatment. That means we have now predictors in terms of patient characteristics, we have cycle data, we have laboratory data, we have omics that come from various sources. All these things immediately scream big data and real-world evidence. So that's why it can be very, very useful. At the same time, we study really outcomes like dichotomous outcomes, which very frequently are rare. Therefore, we need the sizes and the volumes. And they can also be temporally distant from the actual exposure, which means most of the times we need to go back in registries and have a retrospective analysis rather than do prospective analysis for these outcomes. So big data and reproductive medicine is here. We've been utilizing it actually quite prudently for many years. We have many publications in terms of safety of the children and the mothers born. The Konartas group from the Nordic countries has done an exceptional job. And we have benefited a lot. We have benefited a lot, and we've answered many questions. And this is, very briefly, one of, the questions where big data and only big data could potentially help us look at. We wanted to look, and this is a paper we published recently, what is the potential, source for the reported increased congenital anomalies risk in babies born after ART. And to do that, we collected essentially all the data from New South Wales, close to 870,000 babies born from around 580,000 mothers in a span of about 9 years. And we divided them in 4 cohorts, whether they had born after ART, after OI, IUI, after natural conception in couples that already had a diagnosis of infertility, or after natural conception in couples that were deemed to be completely fertile. And this is a very busy slide. Please don't, just read the 2 colored boxes. So ART-conceived infants had a modestly elevated risk for major cardiovascular congenital anomalies, major genitourinary congenital anomalies, and major urinary congenital anomalies. And that is when they were compared both with the natural conception infertile control infants, although these risks were attenuated. And that means that we now have at least indirect evidence that to an extent, obviously we always thought that it's the population that potentially will increase these risks, but we know that there's certainly an element of the medication we give. And at the same time, and the other types of interventions we do, and at the same time, when we compared ovulation induction in IUI babies, then again we found that the overall major congenital anomalies risk and some organ-specific congenital anomalies were again elevated compared with both the 2 natural conception control cohorts, which once again suggests that it's not all in the underlying population. There is probably a contribution of the interventions we do, and because with IUI we just have very minimal interventions, it might be the medications that we give sometimes during the actual pregnancy or during the preparation of the cycle. Another very important effect, and this has been very well recognized, is that ICSI was associated with a higher risk for major genital congenital anomalies and minor urinary congenital anomalies and hypospadias. And this is something well known. This is nothing new. However, what we were able to potentially contribute to the literature is the fact that even after accounting for parental infertility by analyzing only ICSI in couples without male infertility, we still found an increased risk of major genitourinary anomalies. And that potentially takes something away from the theory that, oh, the reason why we have hypospadias in ICSI babies is because the dad had some form of dysfunction in their genital system, which then affected the baby boys. It's likely that that's the case for a significant part of that risk, but not entirely. We actually have evidence that the actual procedures that we do might be linked to that as well. Another interesting bit where real-world evidence might be helpful, and some of this data have been presented previously by Biljana, so I won't just insist, is gonadotropins and what RCTs have shown, whether urinary gonadotropins with recombinants seem to have a difference, and most suggest no, they do not, with the exception of the Van Velde systematic review, which is actually quite old, more than 15 years ago, which suggested that there is a marginal lower pregnancy rate with recombinant FSH compared to HMG. At the same time, for the originators, we know they produce similar number of oocytes. However, the most recent systematic review that we published in Human Reproduction suggests that, unfortunately, they lead to inferior live birth rates compared to the originator. So, again, I won't stick here. This is essentially the French study that Biljana suggested. It has been published by Michael Greenberg. And, it's quite extensive. It involves the entirety, more than 99% of people who live in France. And, these are the distributions of the different gonadotropins that were used. And the purpose of, obviously, of this study was to compare the outcomes between the different types of gonadotropins. Something that needs to be discussed is that this is one of the very few studies in terms of real-world evidence where you could clearly see that the authors did a very, very honest attempt to control for as many confounders as they could get their hands on. You can see here age, center type, whether pretreatment was used, the number of previous IUIs, the number of previous egg collections, the year that the egg collection was performed, previous miscarriages, previous ongoing pregnancies. Yeah, it's not a complete list, but definitely you can see that some major confounders are already there. And more than 240 stimulations. And what are the results? The results have already been communicated by Biljana. You can see a 7% lower odds of live birth with urinaries compared with the recombinant alpha originator, and 11% lower odds in terms of cumulative live birth. And these seem to be independent of the age and the type, the strategy. And the same applied for the biosimilars, where you would see a 19 and 14% reduction in the relative odds for live birth and cumulative live birth when you compared the biosimilars with the originator. And this is actually quite interesting. Why? Because the numbers are so close to the numbers that we have published by analyzing only randomized control studies evidence. And this is, again, was independent of the stimulation. So it's the same topic. So how can this data now be sort of incorporated in this cycle of research diagram? It's up here. What they can do is they can confirm RCTs, and if they are not confirmatory of RCTs, then they can lead to hypothesis generation. And when this hypothesis is generated, in an ideal world, we would need to validate it through properly conducted RCTs. But as we said, there are significant challenges, and I'll devote the last minute and a half of my talk to how can we face the analytical challenges of big data. So we already have heard talks about artificial intelligence, and people think that that's a match made in heaven. And the truth is that that's actually quite close to being true. However, we need to be able to evaluate artificial intelligence, and I'm just borrowing something from the cover of The Economist, where artificial intelligence is not a magical solution, it's not a magic bullet for everything. It's not an angel nor a demon. And the same principles apply. Garbage in, garbage out. Remember that. Just because it's been analyzed by some machine learning model doesn't mean that all bias has sort of been nullified. It is very, very common in machine learning models to find completely spurious results. If you would like to be entertained, I mean, probably you'll say, Christos, this is a very weird sense of entertainment you might have. I would ask you to go to this website where this guy, who's an epidemiologist, has hundreds of examples of spurious correlations. So here you can see how it's almost identical. The bachelor degrees awarded in engineering, how it correlates with electricity generation in Cambodia. And I can imagine that most of you would say that it's unlikely there is a causal relationship there. So AI can predict, but can it help us make decisions? Well, AI can process large amounts of data at vastly greater speeds than what we can. However, it will be trained based on data we have generated. Therefore, it will be limited by the biased decisions we have made. So always have that in mind. Of course, they rely heavily on the quality. AI relies heavily on the quality of the data we provide. Not all AI is created equal. Machine learning is, essentially very efficient, but it's a very efficient regression analysis, so it's nothing magical. And in many cases, AI can detect spurious associations, and we still need to just be very critical about the results we find and we see. So to conclude, the take-home messages, and thank you all for staying, is that RCTs are currently under attack as they have been challenging to conduct and therefore have not really transformed clinical practice. Big data and real-world evidence, real-world data have recently gained a lot of traction as a potential alternative source of credible evidence. Their strengths include increased statistical power, obviously, coming from the real world and being comprehensive enough to also potentially capture the effect of genes, different environments, and so on. But their weaknesses include the fact that they have large computational needs, and potentially due to their heterogeneity and their veracity and the fact that they're not clean data, they can lead to biased conclusions. Reproductive medicine is a field that could greatly benefit. We already have started seeing such approaches, either in the field of safety or in the field of efficacy of certain products. And obviously, artificial intelligence is something that we expect to completely transform the field. But once again, we need not to jump on the bandwagon too quickly, to exercise common sense and caution and good research practices. Thank you.